Here we are for part 2 of hyperbolas. I divided this one up because there's so much here to pay attention to. Here's our general equation of a hyperbola, which pays attention to where the center is. Center would be at HK, which looks like, at least in this case, let me see if I can, yeah, this looks like a 5 by 5 grid. Notice 1, 2, 3, 4, 5 gets us to negative 25. So at least on this one, it appears that our center is at 0, 10. And because this is positive, we see a transverse axis, which is horizontal. Had the y term been positive, we would have seen a transverse that was vertical. It's probably worth it when you're first looking at an equation or considering it to write off, make some designation to help you remember where your transverse is. Now, the special case where the center's at the origin makes for a much neater looking formula. The focal radius is the distance from the center to the focal point. It can be calculated, if you know what A is and you know what B is, it can be calculated by squaring A, squaring B, adding them together, and then taking the square root of that. We know that the constant, when we talk about this geometrically, the absolute value of the difference between the distances of any point on the hyperbola to the foci is unchanging, and it is equal to the length of the transverse axis. So let's pick up where we left off, which is right here. We're going to transform the quadratic relation equation, which is in standard form. See this, x squared, y squared, xy. So we're going from squared terms to linear terms to a constant term. We're going to put it in the general equation of a hyperbola. And the two forms that we have are right here, with this one being a horizontal transverse, and this one having a vertical transverse. Let's see what we've got here. We know how we do our transformation, don't we? We write it up here. First thing we do is we get the right side to equal 1, and then second we get the left coefficients, at least in the numerator, to equal 1 of those squared terms in the numerator. If we follow those two rules, we'll always get it right. Isn't that nice to know? So I'm going to start by subtracting 589, and that'll give us 25 x squared. The other thing I'm going to do right now is I'm going to put my x terms together, minus 200x, and I'll put my y terms together, not minus 9y squared minus 36y equals a negative 589. it's pretty clear. I'm going to have to divide by a negative to get this to be a positive 1. Oh, looks like an X. Forget that. Let's see if I can... I'm having trouble. So just to remind us, these are both going to be positives in the numerator. Alright, so this would put this over a negative 589. This over a negative 589. And then maybe I should extend this. Alright, so what do I have right now? I've got my 1 over here. I've got a mess, actually, haven't I? Let's see. We could look at this as the whole thing being negative. Negative. And say 25 x squared plus, oops, sorry. I just took this negative and moved it. So underneath here I have a positive 589. And nothing changed in my denominator. And this, if I look at this, I've got negatives in my numerator, I've got a negative in my denominator, so I could rewrite this taking out the negative in my numerator. And taking out the negative in my denominator, I got negative over negative, which gave me positive 589. I'm getting closer to where I need to be, but we do have this inconvenient problem right here, don't we? The linear terms. So this tells me I need to complete the square. I'm actually going to abandon what I've done, all of this. This was enough to show me that I need to do some completing the square. So let me pick up, I'll change to a different color, and try completing the square before I do anything else. So I've got 25 x squared, and I'm going to pick up this negative 200. Oh, right. 25 x squared negative 200 x. And I'm going to want to add something to that. I just don't know what at the moment, because I want to have a perfect square trinomial. And then what have I got here? A negative 9y squared, negative 9y squared, and a negative 36y. There's something I'm going to add there. I'm going to get this out of the way, so I'm going to subtract that from both sides. Completing the square is going to be very messy unless I get this leading coefficient to be 1, which I can do by simply factoring out 25. Yes, my laundry's done. All right, plus some number, which I'll get to in a moment. I have the same problem here. I'm going to factor out a -9, which will leave me with, this is very manageable, isn't it? And this will be a positive. I'm going to add some number there. Now I am remembering that I've got an equation going on here. All of this is equal to something over here. Now let's figure out what the perfect square trinomial would be. Thoughts? Remember what we do? We divide this in half and then we square it. So that would be -4. We square -4, we get +16. And now I am out of balance. I didn't just add 16, did I? I added 16 times 25. Whew. That's a lot. Well, 4 times 25 is 100, so 16 times 25 is 4 times larger. I just added 400 to the left side, so to keep it in balance, I need to add 400 to the right side. Over here, I divide by 2, gives me 2, I square it, I get 4. Looks like I added 4, until I look at my multiplier, which was a -9. I didn't add 4, I subtracted 36. Do you agree? All right, I think I better extend the page. This is going on and on. Now let me try to clean this up a little bit. We knew we were completing the square because we wanted a binomial squared. What does that binomial squared look like? True? And then here we've got y. And all of that is equal to, what happens when I put this all together? I've got a positive 400 and a negative did I do that right? 6 and 9 is 15, carry 1 is 12, carry 1. So that was a -625, and I'm going to add 400. You're probably using a calculator and you're there already. So this is actually a -225. And one of the things you may notice, I'm noticing it, is that 25 times 9, it's -225. I think this is going to help us. Now, I'm going to go back up to the top of our screen here. Remember what we were going to do? We were going to get the right to be a +1. We started doing it. And get the left coefficient to be a +1. And we started doing that as well until, we said, no, we've got some other work we need to do first. We have to complete the square. So maybe we should add something here, which is, how could I say it? Perfect square. Could I just do this? Trinomial. A perfect square trinomial. Will that remind us that we want to do that first, then go to making the right member 1 and the left coefficients 1 as well. Okay. My laundry has to wait. All right, so we know what to do. We're going to divide everything through by a negative 225. Could we have completed from up here? The answer is yes. Would it have been unnecessarily complicated? Yes. Better to do that, completing the square, before you go into steps 1 and 2. So now I have that right member. So we did this. Now we're doing this. And finally, the left coefficients need to be positive 1. Well, if I divide top and bottom by 25, I get a coefficient on my squared term of a positive 1. And down here I'll have a negative 9, right? And then I've got up here y plus 2 squared, and if I divide, oh, this is going to become positive, and I'll have 25. So I think what I should do is move this negative from right here to here. Now what does this tell me about how this thing is going to graph? It's going to have a vertical transverse. The center is at, you tell me, the transverse axis. My A is equal to 5, so my transverse axis is 10. My conjugate axis, my B is 3, so that's going to be 6 long. And where is C? Remember, C squared equals A squared, which is 25, plus B squared, so C is going to be equal to the square root of, this is not very pretty, is it? If I add these together, I get 34, so square root of 34. Now when you go to graph, knowing that C is the square root of 34 isn't particularly useful. That's approximately, well, I know the square root of 36 is 6, and the square root of 25 is 5, so it's somewhere between 5 and 6, and closer to 6. So you would do this on your calculator. I'm just estimating. That's an estimate. It might be 5.9, I don't know. Okay, so let's see what we were asked to do and see if we've done it. Transform the quadratic relation equation, which is in standard form right here, to the general equation of a hyperbola. And you can see how useful it is to do that, because once we did that transformation, we knew so much. We knew which way the transverse went. We knew the length of the transverse, the length of the conjugate. We knew where the center of this hyperbola was. So here it is. Let's graph it. We'll start with finding the center. That's at 4 and -2. And the transverse is a positive term, and it's vertical. So I'm going to go 5 away from my center. 1, 2, 3, 4, 5. Whoops. And 5 away from my center going the other direction, so right there. And then to make my box for my asymptotes, I'm going to go over here to 3, 3, and let me put in the corners of my box. That's really all I need are these little corners. So I don't have to mess up this drawing too much. Now I'm going to draw my asymptotes, which I like to do in red. And again, you would use a ruler. And you don't actually have to have a ruler. You could use the side of an index card or something that's straight. Oh, you can see why you should do it, can't you? Now I'm going to draw it. Let's have me do it in green. I know my vertex is here and here. I also had figured out what my C was, didn't I? We used this formula, and I figured it was almost 6. So that's from the center. 1, 2, 3, 4, 5. It's about here, just below that, and just above this grid. And I'm going to draw my hyperbola around that, approaching. It shouldn't be going over it. I'm sorry about that. And it should be curved, not jagged. I'm sure you can do a much better job than I can with this awkward stencil that I use. All right. Stylus, I should have said. Yes, if you could see me here in my recording studio. Yep. Is that how you spell stylus? Oh, well. All right, so let's summarize. The geometric definition for a hyperbola, set of all points for which the difference between the distances from the focal points is a constant. And we have all the parts here, right? We have the transverse axis with the vertices at either end. We have the conjugate axis, which serves to help us know just where to put our asymptote. Gives us the little corners of the boxes so we can draw our asymptotes accurately, because once we have the asymptotes drawn in, drawing the hyperbola becomes fairly simple. Here is the standard equation. We're not going to do anything with this in this course. In your next course, pre-calculus, or your college course, you will probably deal with this. What this xy term does is, instead of everything being exactly horizontal and vertical, it rotates it a bit. So it gets even more interesting. Done. Now this one is worth a couple progress points. About time, huh?